All right, thank you. Okay, welcome everyone. I know most of the people here. There's a few unfamiliar names. If you don't know who I am, I'm Colleen Craig, and I'm an associate teaching professor in the University of Washington Department of Chemistry. And I really want to thank everyone for tuning in for our first chemistry education group seminar of this academic year. Before we formally get into it, I have one small piece of housekeeping. I'm curious to know, since this is a relatively new series, I'm curious to know where you heard about this seminar. So if you could please put this URL into a browser. Oh, there we go. And the poll is activated. And please let me know if you have trouble opening it. And I'm just curious if, email from the chemistry department or from another listserv or from me or from another colleague. Okay. All right, I'll just leave that open while I give the rest of my intro. So before I introduce our speaker, I'd like to acknowledge, as the University of Washington and any attendees we might have from other institutions, the Coast Salish peoples of this land in the Puget Sound region, which touches the shared waters of all tribes and bands within the Suquamish, Tulalip, and Muckleshoot nations. So thank you for that. And with that, I am thrilled to be hosting my friend, Professor Jack Barbera from the University of Portland, down in Portland, Oregon. I've actually known Jack since our chain wallet days in the late 90s when we were undergrads at the University of Colorado at Denver, part of a about 10 member class of chemistry majors at that time. So Professor Barbera now is Professor of Chemistry Education at Portland State, as I mentioned, in Portland, Oregon. He leads an active research group focused on how students learn chemistry, how psychological factors such as motivation and mindset influence that learning, and how well our methods to measure student learning and psychological affect accomplish these tasks. Throughout his career, Jack has been a leader in the application of methods from statistics and the social sciences to the analysis of chemistry education data, and has really raised the bar for the rigor expected in chemistry education research. Today, he's going to tell us about how to conduct educational studies that produce meaningful data, which can be analyzed rigorously, and thereby provide meaningful inferences about the efficacy of an instructional practice. With that, please welcome Jack Barbera.
Great. Thank you very much, Colleen. Let me just 1 second to make sure that I share my screen appropriately here. Right. Colleen, you can see the appropriate slide now. Great. Thank you so much, Colleen. It's great to be here virtually. Maybe someday I'll make the couple-hour drive up the highway and get to visit everyone in person. But for now, hey, at least I get to give a seminar this term while I'm on sabbatical, and I'm glad to take any and all questions. I know we've got plenty of time afterwards, so that there's things that come up, jot them down. We can go back through slides, whatever it is. This is not as much of a researchy talk as I typically give. I want it to be kind of a broad overview of why we do the things that we do. It's not about any one specific project, and that'll make a little bit more sense as we go through here. Let's see. Come on, advance. There we go. So as Colleen said, I run a chemistry education research group down here at Portland State, and I've been doing this. I've built a whole career on basically developing and evaluating different type of assessment tools and applying them to understanding teaching and learning within chemistry. I'm happy to say this is my first year as a full professor now. I've just recently been promoted, and so I'm glad to kind of be at this point in my career. The mission of my group is to produce high quality data about educational outcomes. And we do that through 3 interrelated goals. Our first goal is about the instruments themselves. So building and robust sets of items, providing evidence to assess those items and make sure that any measurements that we're making are the best data that we can get, and that'll make a little bit more sense of what that means and why we do that as we go through the talk. The second big goal for the group is taking the instruments that we develop, other things that are out there in the literature that have a lot of evidence behind them, and using them in some level of investigation of the impacts of different learning environments. You'll see, kind of the frameworks of one of those projects today. And then finally, kind of in the, the more senior years of my time as a faculty member, the third mission now for my group is to increase the capacity of the chemistry education community as a whole for conducting evidence-based evaluations of teaching and learning. So my talk's going to end on a positive note, which is this goal 3 of when we get to the end, I will tell you about one of our grant-funded projects to kind of reach out to a lot of other people to be able to hopefully improve the evaluations and assessment that they do in their own teaching and learning or in their own research projects. So with that, the bulk of today's talk is going to kind of focus on starting with the framework around a goal 2 project and tell you a little bit about how we do things aligned with goal 1 to support that project. That's going to end on a little bit of a negative tone, and then we'll bring it back to a positive thing when we get to goal number 3 at the very end of the talk. So to start out, we ask a lot of this question here in most of our educational research. So I have something I want to change about my course, or my colleague wants to change something about their course, and they want to see some change in a student outcome. And so we can ask the simple question: if I make change X in my course, does outcome Y improve? And we see a lot of studies that people tinker with something and we say something about our students go up. Now, these are perfectly legitimate questions, and these have led to some great things in our community. However, if I step back for a moment and tell you how I got here to be a chemistry education faculty member, I actually have a dual PhD in physical chemistry and in chemistry education. So as a physical chemist, I was never taught to just say, oh, I can tweak this variable and I see this change in another variable. I was taught to understand, well, why does that happen? That's the same way I approach education research data. So a more important question for me is, how does a change in X impact outcome Y? So that if I get the expected outcome, I may have more information about why it's working. Or if I don't get the expected outcome, I have more insight into why it doesn't work and I can make improvements. To take that a little bit further, we can say, are the mechanisms for the impact of whatever X is on Y the same for all learners? So there's been some great data that's come out of the University of Washington of disaggregating course level data and seeing what things are working for different learners. And we have to understand that maybe the same mechanisms don't work for all people, and maybe we need to be supporting things differently for different groups within our classroom, so that we're not just talking about aggregated results. So the way that we model things really gets at these mechanistic levels of not just does Y improve, but how it improves and how the same outcome could be supported in different ways for different learners within our courses or in our research studies. So one of the studies, one of the projects that we've been working on for a while is implementing what's called the self-system model. And the self-system model helps us connect sort of what are the things that are in between what we do in our course or the course context and what we want to see in student outcomes. So in the self-system model, the kind of things that are in between there are what are called the self-beliefs and the actions of our students. And I'll go through each one of these in turn to give you a little bit of insight into what some of the variables are within these, this sort of cartoon picture of this model. Within the course context, we look at a variety of things. We can do course observations and have some information about the structure of the course, how it's facilitating, how things are facilitated within the learning environment. We can pull artifacts, exams, looking at what we actually put in front of the students and what we ask them to do. And so that would be all like observational qualitative type of data. And then we make a lot of measurements with the students. So in these next couple of slides, anything that I have in italics are actually data that we collect in self-report assessment instruments with students. So one of the things under course content is getting a sense of students' perception of the environmental entity. So you've all probably heard of mindset beliefs for an individual, but a student's perception of what is the environmental entity of the course itself. Does this instructor think that everyone in this course can achieve? Or is this course really being tailored to the people who have already come in with a lot of background knowledge and maybe not all learners are going to be successful in this environment. That's called the perception of environmental entity, and we can get self-report data from our students for that. The other big thing that we look at in course content are whether students feel any sort of stereotype threat. And we look at stereotype threat both with regards to race and ethnicity, as well as with regards to gender identity. And we look at how those interact in terms of what students are picking up on and how it might affect what they think about the course environment itself. This is actually the basis of a PhD project for my student AJ. AJ is just starting their second year in the program here. We just got a bunch of data out of not only our institution, but another institution to kind of get AJ steeped in some of these measures and how they're functioning and how we can start building these into some of the projects that we're working on. We move a little bit forward in the self-system model to the self-beliefs portion. The self-beliefs are covered by a variety of different ideas. And so we look at things like the individual student's mindset. We look at their sense of belonging. And because the self-system model, the outcomes are framed as course level outcomes, and we're looking at course level sense of belonging, there are other research projects that look at sense of belonging to, say, a major or to a university. Those are related to sense of belonging at the course level, but we feel that instructors have less control over student sense of belonging, say, to the university, as they do to a sense of belonging to their actual course or the type of learning environment they're trying to support. And then the last thing in the self-beliefs are a variety of different motivational aspects. The two most salient ones for our work are self-efficacy and then student task value. I have a number of collaborators in this area where we're looking at self-beliefs. I have an NSF-funded project with Swazette Mooring at Georgia State University, and Swazette and I and one of her graduate students are looking at how we actually define and measure mindset when it comes to chemistry, and whether we talk about chemistry intelligence or chemistry ability. We had a paper that recently came out in the Journal of Chemical Education a few months ago that sort of set the stage for just the language that we use in talking about mindset with higher education STEM students. And we've got some quantitative data that we should have some papers coming out in the next few months or so as we get through processing it. I'm working on some sense of belonging measures and analyses with Regina Frey at the University of Utah. Regina has several papers in publication in both JCE and in SERP on student sense of belonging. We're taking the measures and the work that she has done in Utah and in her prior institution and expanding them a little bit in terms of the measurements themselves of sense of belonging, as well as modeling some of the data with regard to the self-system model. Then I have a long-standing relationship with Michael Phillips, who's a psychologist at the University of Northern Colorado. We've done a lot of work over the years in different ways to measure motivation. I have a lot of different instruments out there in the literature around motivation with a couple of different theoretical frameworks in the area of motivation research. So that's been something that Michael and I both started at University of Northern Colorado together a number of years ago. And so that's been a very fruitful collaboration outside of chemistry education. Moving on to the actions phase. So the actions phase of the self-system model are framed by two big ideas. And one is students' expectations for and buy into the things that we put in front of them in the learning environment. So if you were going to do something active in your classroom, then we have to help align the expectations of our students for what functioning in an active learning classroom looks like compared to functioning in a straight lecture environment. And we also have to do some work to try to get a sense of what is their buy-in to engaging in whatever it is we put in front of them. We can come up with the greatest activity in the world, but if nobody engages, if nobody buys into that this is a useful thing, then it's not going to be a useful tool for us to help teach them. The corollary to that is looking specifically at their engagement. So once we put that in front of them, how do they actually engage with the learning environment and the resources we give them? And there are a lot of different aspects of engagement that we look at. So behavioral, cognitive, emotional, and social. We've got a couple papers out there in review right now on some of our engagement work. This is led by several of my graduate students. Elizabeth is a third-year PhD student in my group, and Elizabeth's focus is on the expectations and buy-in portions of this project. And then Nicole is a fourth year, and Safa is a third-year PhD student in my group, and they're both working on different ways to look at student engagement from some of the learning activities that we do here at Portland State. And then finally is the end of the outcome piece of the self-system model, our student outcomes. And we use very traditional student outcomes. So we're either looking at individual course performance or we're looking at persistence in a course series. Other people conceptualize this differently. Maybe we're looking for conceptual understanding or skill development. It's these we tailor more to the learning environment that we're studying and what the instructors feel like are the salient outcomes for what they're trying to do. So typically, we still stuck with kind of the more traditional, what does it look like in terms of course or exam performance, and kind of breaking things into formative and summative at best. So when we put all this together, now we have sort of a trajectory or a model of looking at, we do something in our course, what do our students pick up on about that in the course context, and how that plays out to maybe what we see in their student outcomes. So we can start to model this data. And this is just a little cartoon picture of a structural equation model. So we take these kind of pieces, we go to the literature and we say, how are these pieces supposed to be related to one another? Or what have prior studies shown about, say, some of the self-beliefs, how they're related to each other. Maybe they're correlated to each other. Maybe one is a precursor to another. And we can start to build these structural equation models. In these models, in the cartoon picture that I have up here, a solid arrow means I expect that there should be some significant relation between two variables. A dotted line says the theory or prior studies show that there should be a relationship here. And so we can put this model in and we can say, how well does our data fit this model? And we can start to look at the paths, the strengths of some of these different paths and their relations. And we don't necessarily expect that all students would necessarily go through the same sort of paths to meet certain outcomes. And so we can see, maybe for some students, a improvement in their self-efficacy is an important part of a pathway in the model. For other students, that may not be an important pathway, and understanding that will help us create different resources and different ways to connect with different students. So one of the things we want to look at anytime we have modeled data like this is that the strength of any inferences we make either at individual relation steps or from beginning to outcome of the model is the quality of the data that we put in at each and every one of these points. And there are a lot of measures that go into looking at a model like this when we're studying somebody's classroom. And again, going back to my days as a physical chemistry graduate student and just a chemistry student in general, we were always told that if we have garbage in, we're going to get garbage out. And I can't expect to have not collect good data, but then have a good, meaningful outcome on the other end. And so that's something that we think about right from the get-go of what are the things that we put in front of our students, how are we processing the data so that in the end we can have the best inferences that we can get out of the type of studies that we do. So this is why we focus as a group on the measurement instruments themselves, because this is the start of the bulk of the data that we get. If we want to plug something into the self-system model, it has to start with a set of items. So if I was to give an item, a simple statement saying learning chemistry is interesting, I would give that to students on an agree-disagree scale like this, and I would ask them to choose. This is one item that then I would build into some sort of forced response instrument where I'm not letting them write open-ended things. These are either agree-disagree scales or multiple choice type items. We then give those to our population. We run some fancy statistics, hopefully someday for me and R, and we can plug that in as an inference into our model. And so this is where we get most of the data that we work with. So we want to spend a lot of time thinking about how do we know these items are functioning, and how are we running these statistical analyses to make sure that we're getting good data and we can make meaningful inferences. So we take a step back and we talk about validity and reliability of data. We know as chemists that we spend a lot of time calibrating laboratory instruments or tweaking analytical procedures so that we generate accurate and precise data. We teach this from day one of general chemistry to our students about talking about accuracy and precision. We do the same thing when it comes to educational measurements. We talk about assessment instruments instead of laboratory instruments. We talk about validity instead of accuracy. We talk about reliability in terms of precision. But all those are the same things. It's just I'm not talking to a bunch of laboratory scientists. I'm talking to a bunch of educational researchers or psychometricians about educational and psychological data. So we're talking the same language, we just use slightly different words. In general, I think about validity as answering this question. Am I measuring what I think I'm measuring about this population? And then reliability is just simply, am I doing this with some sort of consistent, in some sort of consistent fashion? And we'll define these a little bit more as we kind of go through the rest of the talk. But it really starts with having support for validity and having support for reliability so that we know we have good data going forward into any one of our models. So we'll spend several slides here talking about how we frame validity in terms of educational research data. Our overarching definition for validity is in terms of what's called construct validity. This is multifaceted. There are 5 different sort of major areas that all feed into supporting evidence for validity when it comes to educational assessments. So we'll start down here on the lower left in terms of test content. For test content validity, what we're looking at is answering this question of what is the content or the ideas that should be covered if I'm going to put together an assessment to capture some construct. And when I say the word construct, that's the thing I'm trying to measure. So if I want to know, say, about students' interest in chemistry is my construct, and I want to know what items do I need, and how should they span some sort of theory if I want to be able to capture the idea of students' interest in chemistry. So we turn to the literature. We do reviews of the literature to see what's been done. Where are we in terms of understanding what it means to have an interest in something? We look at different theoretical frameworks. We interview faculty, we interview students, we interview people in this area of psychology that do these types of studies. We can do observations. There are a lot of ways we can start to define the space depending on what construct it is. We've done things in terms of students' understanding of thermochemistry. So we would do different types of interviews or different types of observations if we were looking at thermochemistry knowledge versus students' interest in chemistry, but it's still setting that landscape for us. This all comes down to basically having a blueprint for our instrument. If I'm gonna assess students' understanding of thermochemistry, then I need to define, well, what's the scope of thermochemistry? Because it can be very narrow, it could be very broad. If we're focusing it at the Gen Chem level, then it's maybe more narrow than if we're focusing at the Gen Chem 1 and the Gen Chem 2 level and not including PChem. So there's not every one instrument is going to cover all scopes, and we define that at the test content level of building and evaluating an instrument. So once we've defined our test content and shown some support for that test content, we move on to the response process piece of evaluating our now newly developing tool. We focus specifically on novice validity. You can frame novice as this is the population we want to study. And I keep using the word novice because this comes back to my days of looking at when we were only talking about concept inventories and the difference between novice beliefs and expert beliefs. And our target populations are always going to be novices. And we really want to only understand how the novices are interpreting our items when it comes to this level. We can get expert feedback in the prior step when we're developing the test content. So here we're trying to answer this question of what information do our novices use when they're trying to respond to some sort of forced response item, whether that's an agree-disagree scale, whether that's a multiple choice item, so that when we give them these types of assessments, we kind of know how they're getting to the different response options. That helps us make meaning of the data and find out where there might be problems in the items that we're using. So to support this type of evidence, we do individual interviews with students, or we run focus groups. The decision is more on the scope of the information we're trying to get. If we're trying to learn something about, students' beliefs about, say, flipped learning, we're going to run focus groups because we want more interactional types of things of what students pick up on in that type of environment, as opposed to how they problem solve in terms of thermochemistry. That might be more informative for us to do as an individual interview. In these settings, we use these to gauge if there's any issues with the wording of the items. If it's a content related thing and we're using graphical representations or figures, are students interpreting them in the way that we want? Do we have distractors in there that, you know, are problematic because we're trying to be chemists and we're trying to put all the detail in the world? That's not really what we need when we give it to students, because what we're looking at, we're trying to get a sense of why students are responding in the way that they do. And when we have all this data, then we review it for themes that we can use to support. Do we have good items that are interpretable by our students, and are they answering them in the way that we expect them to answer them? So we start to group our data together. So I put this slide together for a talk about specifically multiple choice option concept inventories. So we would say that an individual's response process, they could be totally correct, which means on a multiple choice assessment, they select the correct multiple choice option, and they can give you the correct reasoning for why they got there. So if it's about thermochemistry, how they solved the problem, and that they did it in the way that we would think that experts would solve the problem. They could be totally incorrect, which means they choose an incorrect multiple choice option, and they get there using reasoning that we've pulled either out of the literature about alternative conceptions, say of thermochemistry, or that we've done interviews on, and we see the common mistakes or the common assumptions that students make that get them down this wrong path. And that's a way for us to know, oh, you answered option B, and now I know how you got to option B. That we have to know that's how students are getting there, that they're following that pathway that we think they're following. There could also be potential threats. So this is when they choose any option, whether it's the right option or whether it's one of the distractors, one of the wrong options. But the reason for choosing that option is influenced by some common yet unintended theme. This usually comes up when we start to throw graphical things in there, or we have multiple sentences that some of them are just red herring distractors that we think we need to build in all of this to make our items more complex, that students are gravitating towards in the lab, or they learned it in another course, and we didn't expect them to be using that piece of information, but it's influencing how they answer the question. And we need to be aware of those so that we're not sending them down a wrong path when we didn't mean to. And then finally, because we're working with humans, we always have to have an other category, because I'm sure all of you've seen students will give you reasonings for an answer and you would never predict it, and no other student would probably give you that answer. And we see the same thing when we're interviewing them, and we really can't ever do anything with this other than we get a laugh out of some of the responses for how students get to some of the answers. So in this, if we have a lot of the first two, totally correct or totally incorrect, those provide us positive support of response process evidence for validity. If we have a lot of the other two, then we've got some problems, and we need to kind of go back to our items and think about, like, are we really, how are we wording the items? Do we need this picture, whatever the problems is that we're seeing, and kind of do the process all over again? And so that's one of our ways that we can support that we know we're interpreting the items correctly with regards to how the students are understanding and answering them. Moving a little bit further through the construct validity is the idea of internal structure. So in order to talk about internal structure, we have to take a methodological journey here into confirmatory factor analysis. So this is one of the statistical modeling techniques that we use, because a lot of the things, when we move away from content, a lot of the things that we assess nowadays are called latent constructs. And a latent construct is just something that's not directly observable. So I keep using this idea of students' interest in chemistry. So your interest in chemistry is not something that I can directly observe about you. I can measure your height. That would be an observable. I can look and gauge your eye color, but I can't look at you and say, oh, you have 70% interest in chemistry. That's not a thing. To do that, I have to ask you some indicator items. And so I have to put some items in front of you, and I have to say, these items are related to this construct, students' interest in chemistry, through some theoretical framework. And this is where those individual items come into play, when I want to be able to group them together and say, this grouping of items tells me something about your interest in chemistry. So I'd write an item. Here's another interest item. I'm fascinated by chemistry. I would ask the students to respond on that, and a strongly agree to strongly disagree. And I'm starting to set up a model for how this individual item is going to tell me something about this latent construct called interest. We modeled this with a simple linear equation. So I started this way because all of our students know y equals mx plus b. This just has an extra term in there, or e is an error term. When we put this into confirmatory factor language, our y variable now is the actual item, is our interest item number 1. Our x variable is the latent construct called interest. Our slope is our factor loading. Our intercept is this tau value. And then our last error term in our linear equation is error within that response. So each one of our indicator items has a linear relation to our latent construct. When we want to measure a latent construct, there are some statistical assumptions that we need a minimum of 3 items for modeling reasons. So we typically try not to have anything less than 4 because 3 is really at the lowest level. So I'll keep my figure at 4 because it's also easy to not have a whole bunch of them in here. So if I really want to measure interest, I need 4 or more items ideally. So each one of these has a regression equation associated with it. And now I have a model that sets up 4 indicator items that are all supposed to have some association to interest. And I can test how well does my data, the information I get from my students, how well does it match this model? And I can model that data and run some fit statistics. So when you see this in papers, we typically present these ad nauseum tables that will tell you about what statistical package we use. So in this case, M+, how we treated the data, in this case with a maximum likelihood estimator. Then everything else are fit statistics that we will then interpret for you and say, these numbers are meaningful to me as a statistician that says, this is really good data fit, or this is horrible data fit, and this is what I'm going to do about it. But that's what we're looking at trying to do is say, now this structure says these 4 items should tell me about student interest. Do they? We do, sometimes very complicated ones. This is what that sort of cartoonish model looks like for an instrument called the Science Motivation Questionnaire that we published a couple of papers on a few years ago. This is a 25-item instrument that's broken into 5 correlated factors. So the curved arrows on the top are our correlation arrows saying that all of these subcomponents of motivation are correlated to each other, and each of them have 5 of those indicator variables. This is an instrument that there's many different wording variants. So people replace the word science and plug in chemistry, or plug in physics, or plug in biology. They use it in different courses and call it the organic chemistry motivation questionnaire and what have you. And prior to us coming along, there wasn't a lot of validity and reliability work done on this instrument to show how well it functioned, or in this case, how well it didn't function when we try to keep doing these wording changes and comparing from one course to another when we're changing up some of the wording. And so that we kind of do this so that if we're going to have, if we want to say we have equal measures across different courses, that we know that our measures actually functioning in all of these different environments. Next in the step through here is looking at what's called consequential validity. So we'll go back to our idea of looking at student interests along our 4 items. And so now we might want to start to ask the question about, okay, I've got this large course. Now I want to start disaggregating my data and I want to start making group comparisons. So if I want to compare the interest of group 1 in my general chemistry course to my interest in group 2 of my general chemistry course, and I want to look at mean scores on these 4 items, I want to know that the similarity or difference in those mean scores is about their actual interests, not about something that I'm doing in the measurement that says that the model for group 1 is not the same as the model for group 2. They can have different responses to the individual items, but the theoretical framework should not be different based on how I define the groups. And so we can test this statistically to say, what is the equivalence or similarity in the models when I have my groups now, my course level data broken out into these 2 different groups, and I can test that. And we would have to go through these number of different measurement and variance tests before we would ever be supported to say, I can now compare either latent means or I can compare actual, average scale scores between my 2 groups. And we can call these groups anything we want. We do this for time series data. So if we have pre-post data, and we want to make sure that the model pre should not be any different from the model post, even though students' interests may change over time, the theoretical underpinnings of interest should not change over time. So we do this when every time we have time series data and we want to say that the change is meaningful. If we're looking at different courses and we want to say students' interest in general chemistry is similar or different than their interest in organic chemistry, again, the theoretical framework of interest should not be any different, even though the responses about what their interest is can be. Or certainly anytime we do this across demographic groups, however we compartmentalize our data, we want to make sure it's not about the model, it's about their actual responses to the individual items. And so we set up, this is the part that takes a lot more sort of legwork on our part, and we try to get large data sets so that we have enough statistical power to kind of make these judgment calls and really interrogate some of the measures that we're working with. Then the last thing in the block is what we call the association with other variables, and there are two big categories under here. So when we look at convergent or discriminant validity, we're trying to answer this question that are the hypothesized relations among different variables upheld? To do this, we have to have variables to compare, and we have to know how they should be compared or not, and we just run simple correlational analyses. So for an example, there's been a lot of work out there about test anxiety, and that the higher your test anxiety, the lower your test performance. So we hypothesize that these are anti-correlated, and if we have measures of both, we would expect that they would be anti-correlated, and that would be one way to support what's called convergent validity. Or if we want to be measuring students' chemistry ability, and we give them a correlational test on reading ability, that we would not expect there to be a correlation between their reading ability and their chemistry ability, or your chemistry test is actually being influenced by their reading ability, and it's not really a measure of their chemistry ability. Granted, within chemistry, they're also learning vocabulary, so we have to be careful about some of these things in terms of, yes, we want them to be learning vocabulary, but as we get further along in the course, they could be still struggling with the vocabulary pieces, not the content you're trying to assess, and really then thinking about what that means in terms of the assessments that we're giving them. On the other part of this is the concurrent or the predictive validity. So again, answering the question, do the results correlate to some other measure of the same construct to either predict a future or a current or a future outcome? So this is just comparing different ways of measuring something. Typically when we see these types of things, are usually in the predictive realm. So we assess something they do in general chemistry, and then we look downstream and see if it affected their performance in organic chemistry or in biochemistry, things like that. And we can start to get evidence of, is this thing we're looking at really a good predictor of this thing that we think it is down the road? And so it's going to take a little bit of time to get both those pieces of data and then be able to try to support that with some sort of positive evidence. I also mentioned that we look at both validity and reliability. So there are two sort of big areas of reliability when it comes to quantitative data. We either look at multiple administration reliability or single administration reliability. For multiple administration reliability, as the name implies, this requires two administrations of the same instrument to the same population. So I put together my first response instrument, I give it to my class, I wait some time, I give it to my class again. When I'm doing that, my administration times are separated in a reasonable time frame that we want it to be short enough that no real change has happened. So if we're looking at student interest, I wouldn't want to wait an entire term or an entire series because their interest in chemistry might actually change. But I also want it to be long enough that when I give it to them the second time, they don't remember, oh, item number 2, oh yeah, I agreed to that one, or I chose option B on that one. We don't want them to be trying to do it from memory. So we have to kind of be careful about how short or how long that time is anytime we do multiple administration reliability. So then we just calculate what's called the test-retest coefficient, which is just a Pearson correlation coefficient across the two time variants, and see how similar are the data sets from time 1 to time 2. To simplify things a little bit, we can also do what's called single administration reliability, which just simplifies the process because we give the one instrument to our class only once. But when we do this, the difference is now, to do this, we have a lot more statistical assumptions that our data has to meet. If we don't meet the statistical assumptions, then that numerical value we get out has very little meaning, because all statistical tests have assumptions, and if they're not met, your program will still run the statistical test, but it doesn't mean that the value is going to be interpretable or meaningful just because your program will run it. So those of you that have um, read any education research data, I'm sure that you've seen Chromebox Alpha reported. Chromebox Alpha is one of the statistics that is used to support single administration reliability, but unfortunately has done so without showing that the data meets the assumptions of what Chromebox Alpha is set to measure. And so we had a publication that came out a couple of years ago of not only framing what single administration reliability is, but some of the limitations of Chromebox Alpha and things that we need to be aware of with the data, and trying to push the community towards other ways of conceptualizing single administration reliability types of data. So usually anytime I give this talk, I put this in because this far into the talk, a question that you might have is, are all published assessment instruments, if I go to the Journal of Chemical Education or if I go to SERP, are they supported by every one of these aspects of validity and reliability? And the straight up answer is 100% absolutely not. And that's not a bad thing. And that's why, myself and some of my colleagues give talks like this. The idea is not everyone has to do every one of these, but as a potential user of any instrument, we want you to be aware of what aspects have been supported, so that if you're looking to do a specific thing with a specific instrument, you know what information I've put forward in the literature or what information the developer has put forward in the literature. So you know how well supported that tool is before you give it to your students and you want to make inferences that might change the way you teach the course, or whether you think that you and your colleagues are really helping your students, that you want to make sure that you have the best data. So this was a very, very quick overview of a lot of things that we spent a lot of time researching about what it means to have valid and reliable data from some of these tools. So this is where we kind of try to bring this back to a happy note in how goal number 3 in our group is going to help the community out a little bit on this in terms of increasing their capacity, so that everyone doesn't have to go through all of the learning process that my PhD students do to be able to run all of these different studies. So I'm currently in the second year of an NSF-funded initiative with 2 of my junior colleagues, Jordan Harshman at Auburn and Regis Compared at San Diego State University. So NSF gave us money to develop and build a centralized assessment instrument resource called CHIRAL. And what this resource will do is we're going through and we're identifying all of the instruments that are used in the chem-ed community. We're cataloging all of their details and all the uses of the instruments so that we have an archive of that. And we're assembling expert panels to go through and review all of the validity and reliability data, so that we can have them write executive summaries about what evidence is there and what evidence we would like to see going forward for some of these tools. And then we're also building a glossary of all the psychometric terms and all the methodology that goes around that. So as a practitioner, when this is up and live, if you're interested in somebody's measure about interest, then you can go and you could read all this information about how this has been supported and make the decision for yourself as to whether this is going to be a useful tool for you to use in your analysis. We just finished up our second round of expert panel reviews. We've got one more to go. With the BCCE coming up next year, we have a launch for the website and lots of BCCE talks and a symposia around this. So I will send information out to Colleen. I'm sure she'll pass it on to all of you. So we expect to be live in early 2022. So that way we're ready for everyone to be plugged in by the time we get to the BCCE next summer. So with that, I don't really do any work in my group anymore other than writing grants and giving talks and being supportive for my PhD students. These are the people that actually do the work in my group. Some of them you saw on some of the earlier slides. We don't have a hybrid 2021 half remote, half virtual picture yet. So this is our 2020 all virtual group picture. And then some of my colleagues that you saw in some of the different slides, these are all my current active colleagues for a variety of different projects. And with that, I will leave you a picture of Mount Hood off there in the distance and a nice evening picture of Portland. I'd be glad to take any questions that you have.
Thank you, Jack. That was very, very interesting. And I'm gonna hopefully get your slides so I can go back and learn where I can dig in. Sometimes when I'm hosting a seminar, I find it difficult to pay attention in the moment, but again, I'm narrating my nerves right now. So let me move ahead and open it up to any questions from the audience. And if you want to raise your hand, oh, let's go ahead. Thank you.
Oh, yeah, thank you. Yeah, thank you very much. That was a really interesting presentation, all things that I didn't know about. And I was wondering if so I had a question when you were talking about measuring something that you do not objectively know. So, for example, a student's interest in chemistry. And if I understood you correctly, so you develop some questions like, I am fascinated with chemistry, between disagree and agree. And then, so you showed us like kind of a glimpse of like the modeling, how one would then weigh which of these questions, I guess, are the right ones to ask, which one tell you the most about whether a student is interested in chemistry. And I was curious if you could elaborate a little bit on how that works. So I can imagine if I knew how interested a student is in chemistry and I know their answers to my 4 questions, then I could run some regression analysis and figure out the answers to which questions are most correlated with the student's interest. But if you don't know what the student's interest is beforehand, I'm just curious how you decide which questions are the right ones. And maybe can you tell us what the right questions are to ask if I want to know whether a student is interested in chemistry? Because I'd be curious.
Yeah, absolutely. So one thing I'll say that we also try to put out there is the amount of time it takes to develop a more generalizable research tool like this. And this is something that when I was starting out as a junior faculty member and starting to mentor PhD students, having to train my colleagues in how much time it takes to do something, right? Because we all know that if we're going to sit down and write an exam, you spend weeks writing your exam. You're going to do it, you're going to proofread it once or twice, and it's ready to go. When we're developing assessment instruments, before we ever even have a pilot version for a PhD level project to do one of these, we're talking 2 to 3 years, depending on how much we're starting with. If we're starting from nothing, 3 years is a pretty good goal to hit, because we're doing interviews, and we're doing interviews before we ever start to have anything that looks like a first response item. So you would ask, how do I know if the students are interested? Well, we have them answer open-ended questions in interviews about what it means to be interested in chemistry, or just in general, and we start to extract from that what I'm hearing from you is that you are interested in chemistry, and we try to use student language in the terms that we would use about what interest in chemistry means. So that alone can be, let's say that's about a year of data collection where we don't even have items yet. I'm just having conversations with you and other people from the target population about what interest in chemistry means. Then we're going to take that along with any theoretical work from psychology and within motivation for interest, and say, now how do we turn this information into actual first level items? We would then write a bunch of item stems. We would get another cohort of students and we would have them talk to us about the items. Here's this item. I'm not even going to give you a response scale. I just want you to read the item, tell me what you think the item means, and tell me how you would answer the item. So then now I have a whole nother set of students that will read an item, I'm fascinated by chemistry, and will tell us, yes, I am, and this is why, or no, I'm not, and this is why. And we look for making sure that if somebody says they're interested, they're going to agree to that item, and we turn it into an agree disagree type of response scale, that we know why students are agreeing or why they're disagreeing with the item. So that could be another 6 months to a year. Now we have items, we have some sort of a response scale, agree, disagree, multiple choice if we're doing multiple choice assessment. Now we take those developed items and we put them in front of another group of students, because now they have the item, they have the response. we get both qualitative data. So we'll do interviews with them again and say, I want you now to spend, 5 minutes, 10 minutes, however long the instrument is, sit, over in the corner of the interview room, take it. And then we're going to go through and we're going to talk about each one. So I want you to read the item. I want you to tell me what you think the item's asking you. And I want you to tell me why you answered the way you did. That's where that whole response process piece comes in a little bit in the way that I framed it out. So now we're looking and saying, oh, you answered agree to this. Tell me why it was agree. Why wasn't it strongly agree, or why wasn't it disagree? So we can start to see, are we getting consistent responses for why somebody is agreeing to something or disagreeing to something? At the same time, we're also maybe doing some pilot versions to get some quantitative data. Maybe I'll give it to one course and get 200 or 300 responses, and I'll start running statistics. So if I just look at, here's a half a dozen items that I all think are about interest, like you said, if I run correlations and I see, hey, item number 4, that one seems to be really low compared to all the other items. Let me look at the qualitative data and see, was there something about item number 4 that maybe students were tripped up because of the language? Maybe a lot of people were on the fence, and so they really weren't sure whether they were going to agree or disagree. Now we've got some qualitative data, we've got some quantitative data, and we can say, you know what? Item 4 kind of sucks. Do we really need it? We've got enough other items. Let's take it away. Or item 4 is getting at a really important thing. How can we change it to make it better? And we might have to go through that process a little bit more. So we would do that before we would ever try to get big data sets to run big statistical models on. So there's a lot that goes into the development. Disagree or multiple choice, that the majority of people are gravitating towards those responses for correct reasons. And we never say that it's that 100% everyone is doing what they're supposed to do anytime they take any sort of first response instrument. But then we play statistical games to try to figure out, how do we reject students' data when we don't think that they're actually meaningfully reading the questions and using the response options.
Oh, I see. So if I understood you correctly, so the modeling requires not just the answer to the 4 questions, but also all the things you just said, maybe interviews or with other cohorts, and based on that, you develop a model which are the essentially important questions to ask, the right questions to ask.
Yep.
Gotcha. Thank you very much.
Yep.
Thanks, Lex. 2 things before I call on Ian. I forgot to mention at the top that we have Jack until 5 p.m. So if there's questions that persist beyond the official session, which formally is ended now because it's past 4:20, but I just wanted to make everyone aware of that. And also, I noticed it when we were getting the Q&A with Let's started. You're still a little bit faint, at least on my end.
Oh, okay.
So just to put that out there.
Is that better?
No.
Is that better? No?
No. Oh.
Okay. No, yes, no.
Is it just, okay, that sounds good.
Is it just you?
Maybe it's just me. Okay, could be. I got some thumbs up from other folks, so we'll move ahead. Thank you very much. Ian,
Okay.
Please go ahead.
I'll say thanks too for the great talk. I really enjoyed it and felt like I learned a lot. This is sort of a follow-up question because it sounds like that process you were describing in response to the first question was rather laborious and time intensive. And it seems great if I could take some of these ideas. I come from philosophy, so sort of a humanities-based discipline, a little bit different than some of the STEM applications maybe that you're talking about. But did you mention that when folks try to apply this to other STEM fields or to some subfields of chemistry, that there were questions about whether they could just copy or paste in different field names, and there was problems with that? I guess the short version of my question is, can I actually steal all that work and just put philosophy in place, or is there going to be a problem with doing that?
The answer is yes and no. And I think it depends on what you plan to do with the data. And I guess it would depend on what type of inferences you wanted to make from the data. I would say, I am probably like everybody else in the room in terms of writing assessment for my own students in my own course. Granted, it probably, because I have years of item writing and an evaluation experience, I might go into the process a little bit differently from the beginning, but I compartmentalize classroom level things and information separately from I'm putting a research tool out there for the general community to use. So yes, I think one of the takeaway messages that I want to come away from all of my talks and all of my graduate students' work is the things that we do are not easy. They are labor intensive, but there's also a reason why then we publish these for other people to use. And this isn't something that I'm only making for my general chemistry course or my physical chemistry course, because the implications are broader than just what it means to my individual students. So that said, depending on what the measure is supposed to be measuring, whether you can take the word chemistry out and put philosophy in, or even whether you could take chemistry out and put physics in, that could change in ways that you may or may not know why it's different. I think the expectation a long time ago was that that was not true. Like, why would it matter? I've got a general questionnaire that's supposed to be about science, but when I put in the word chemistry, why wouldn't it function any differently? I'm doing this in a chemistry class. Well, we have qualitative data that says, if we're looking at the chemistry class, and this was actually qualitative data that we did here, what do you think the average major is for somebody taking my 400-person general chemistry class? They're most likely a biology major. A very, very few of them are actually chemistry majors. So I'm asking them about their science motivation. When I ask them, what does the word science mean to you when we're in an interview? They tell me, oh, science is biology because biology is the thing I care about and that's my major. Very few of them mention anything about science in general the way one of us might answer it. And very, very few mention it specifically contextualized around physics or chemistry. So when we're actually asking them a science motivation question, if we were to replace science with biology, then those instruments probably function very well when we're collecting data in a classroom like this. But if I ask them the science version and I ask them the chemistry version or the physics version, those are most likely going to be very different because they think about science differently than they think about chemistry or biology if they're a physics major or if they're a biology major. So it's really hard to say when it's going to work and when it's not going to work because you have to have a bigger understanding of the population that you're trying to probe, and that science and biology may be more similar to each other than science and chemistry or science and physics to them when we're looking at their motivation or their interest. So, and that was kind of one of the big takeaways in the series of papers we published about that instrument is, no one's ever asked the question. So yeah, why wouldn't we think that some of these like that they should be plug and play? But as soon as we start seeing that the models don't fit anymore, we have to start asking why doesn't this data work in the same way it worked over here? And then we have to go start from quantitative data and go to some qualitative things and really start to get some student insight into why they're thinking about these two things differently.
Thanks, Ian. Are there other questions? Claire, please.
Hi, so I just had a question about, and I think you kind of covered this throughout the talk, and especially, what you're talking at the very end about making this sort of database, all these different instruments. But I'm curious if you could elaborate a little more on comparing two different instruments which are created to evaluate the same thing, say, interest in chemistry, and how, how you would compare it, like you said, the validity and the reliability of those two instruments.
Yeah, I think the things that I look for, and this is, when I'm reviewing papers or when I'm reviewing grants, like some of the starting place that I would like to see a lot of people coming from is something front loaded that was qualitative, that I have some insight into what these items mean to the target population that I'm trying to evaluate. It's the rarer case that we're going to see people doing like full measurement invariance for a lot of reasons. but there's really no reason why somebody that wants to develop an instrument can't do some level of qualitative insight into what's meaningful in the target population before they ever do anything with the individual assessment. So when if I found 2 or 3 instruments that were all measuring similar things, I might look in to see, hey, how was this one developed? You know, do they differ in the way that they started the process? And I will be honest, I've been, you know, I forget, well, do the math. I started my group in 2007. So I was a PhD student starting in 2002. So prior to 2002, the way that people develop instruments, and this is not a slam on my senior colleagues, this is where the field was in terms of what we understood about measurement and statistical analyses around these types of things. If I want to write a chemistry concept inventory, and this is how we started out for thermochemistry, I'm a physical chemist. I should certainly be able to sit down, and my PhD students should be able to sit down and write 12 items on thermochemistry. We should be able to look at them and say, yep, those look great. Let's put them in front of a bunch of students. Why wouldn't that make sense? Well, because I don't think like a general chemistry student that is just learning thermochemistry anymore. Neither does my 3rd year PhD student. So while we may be able to start that process, when I put an item in front of an individual, I don't know what they've learned at that point. I did at some point, but you know, our memories aren't as good as we think they are from when we were actually a learner in a course. And I think that's the most basic level to secure that our items are meaningful in the way that we think they are meaningful to the population we're trying to analyze. So I would kind of build sort of what are the most salient things that I want to look for, and I wouldn't expect every instrument to hit all of those milestones, but there are some that would be more meaningful than others. If they were latent constructs, so if they weren't concept inventories, they weren't content based, I would want to see some level of either exploratory factor analysis, which I didn't talk about in terms of how items are grouped together, or some sort of confirmatory factor analysis, because what we typically do, whether it's a content test or whether it's something in the affective domain like motivation or interest, we take the items and we calculate an average score. And we want to know that, what does that average mean? That a high value means you have more of something, a low value means you have less of something. But if the 5 items I give them about interest aren't really related to each other, if I have that item 4 that just doesn't work well, then that if I keep it in my data set, then it's going to influence that average. I'm trying to make meaning out of that average. So if I don't know that item 4 functions poorly and I should take it out, then what does that do to my average? And then is that average even meaningful? So when we start to work with latent constructs, the other thing that's really important is, have they done some level of structural pieces, either confirmatory factor analysis or exploratory factor analysis? And the difference in those is really, again, model that you can test, or have to start and you don't even know what the relation should be when you're just starting out.
Cool, thank you.
Yeah.
Other questions? I've got one. Just following on, you know, the questions around that Lutz started us off with, thinking about how do we connect the measurement to this latent construct or the latent variable. And this is something I've always wondered about when it comes to confirmatory factor analysis too. And the way you described like the process of developing a new instrument, of like interviewing students and knowing like from the ground, like what is the student interest, like that all makes sense. But when I first, and I didn't know that's how that worked, so that's really cool. But when I've learned about confirmatory factor analysis the first time, it seemed to be something you would apply to a survey that had already been established by someone else, that you would apply to a new population, and then you would confirm that it's measuring what you think you're measuring. So then in that case, what is the interest measurement if you're not the one actively doing, if you're just using the survey and you're not doing that qualitative piece?
Yeah, then I would say looking for, so let's say you found an instrument that was like that, then it's really then having some insight into the theoretical framework that was used by the original developers
Okay.
to say, okay, you pull my paper on interest in chemistry, and you want to use that model of, I said, here are some items and they're all supposed to group together, and here's these other items and they're supposed to group together.
Right.
That yes, you were starting with an a priori model and you can run a confirmatory factor analysis,
Okay.
but I would always ask my graduate students to say, okay, well, what came before that? How do you know that I did good work? And that's some of the problems when, you know, we publish in the chem ed literature that maybe my original work came out of educational psychology and somebody's not going to necessarily go to the original journal, but at least having some insight into did I do right by coming up with that model in the first place,
Right.
if I didn't develop the theory. And so a lot of that is then looking at, you know, what led up to that model that is now your new a priori model. If you're not going to go through the interview pieces, which I don't agree that everyone necessarily has to, we start that way a lot of times. This is already a known theoretical framework. We have relationships here. We can go right into a confirmatory factor analysis framework.
Okay. I see.
Yeah, but I'll tell you the backstory to that science motivation questionnaire data, that when we really started digging into the theoretical framework that they used and how that instrument developed over time, there were a lot of holes that we couldn't nail down of decisions that were made through like 3 or 4 generations of the instrument before it got to their version 2, which is the one that's the most widely adapted and the most widely used. There were a lot of holes that we can never fill in, that they were making decisions that didn't seem to be supported decisions. It was just, oh, well, here's this thing, and well, these are our new set of items, or this is our new factor. And we think that that's a lot of why it doesn't work now, because they've changed it so many times, but it wasn't really theoretically supported, some of the changes that started making beyond the initial sort of setting up of the instrument. And then, but once it's out there in JARST and it starts getting used, I mean, you know, all bets are off.
That is so helpful. That really clears up a lot of things I've been confused about for a while. So I also had this impression that every time you collected data with a survey, you should always do a CFA. Is that true, or is that not true?
I'd like everyone to do CFAs, but
okay,
you know,
so that's
I'm realistic.
Okay.
Yes and no. I mean, you know, I think again, when I'm reviewing a paper, if I'm reviewing a grant or something, or we're developing something, you know, with somebody else, it's how far removed from the original population are you?
Right.
Right. So, you know, if we've already developed something in our Gen Chem class here and it was 2 years ago and we're gonna use it again, it's gonna be a different population. Or if we're, you know, well, how far removed from the original is it really that vital if you don't have the N? If you have the N and you have the means to run a CFA, by all means do it every time.
Got it.
But if you need 250 students or more, then you know, now that becomes problematic to say everyone has to do a CFA. So we try to set the limitations of, like, we always do them, but we always work really hard to get big data sets to be able to do things like that.
Yeah.
So I don't, you know, review too harshly when somebody doesn't do it in a publication or isn't proposing to do it in a grant, given the size of their population or the instruments that they're starting with, and whether they have any data that preceded them wanting to use them for their study. So, but yeah, if it's something that's never been used in, say, higher ed general chemistry, then absolutely, you know, you've got to do something to say that this is still functional in the way that you think it's functional.
Okay.
Yeah.
Yeah. Okay. Sam and I are surveying a bunch of students this quarter for a project, And we're using a survey that had been used in Gen Chem in our courses before a few years ago. And the woman who wrote the paper did a CFA. But yeah, and we used it just because we had previous data, like pre-pandemic, just to compare against. But I was a little like about using it again. Fingers crossed. It works out okay.
Yeah, and that whole pre-pandemic, post-pandemic, depending on what it is you're trying to measure,
Yeah.
That's where like some of the underlying assumptions may no longer hold.
Okay.
But I think that that's going to be such a problem for so many people that I think if you have a longstanding instrument that's been used in your department, and you can say, look, the nature of this course or how students get into this course, as long as the requirements haven't changed, you guys have big enough courses to say the year-to-year variation is pretty similar. So we know that if we're using this instrument and we've had good data, that when we're seeing dramatic differences or all of a sudden our model doesn't fit because now, well, things are different now and they were way different last year, that you could probably chalk it up to that's a real difference in what we're now measuring about the students, not that this tool no longer functions. I would have, well, I went out on the limb last year and I didn't change any of my PhD students' projects very much because I was like, oh, COVID, come on, 2021, we're going to be great. We're going to be back to collecting data. Yeah, now we're looking at like, well, now what do we do? We've got another year of like half and half or, different expectations. So yeah, who knows?
Shit.
What are you surveying them about?
It is a 4-part survey with, oh, wait, I'm sorry. It's been a while since I looked at it. It's a 2-part survey with one part is on expectations about learning chemistry. I forget exactly how we worded it. And then another one is got 4 subparts on mindset, belonging, relevance, and self-efficacy, I believe.
Okay.
And that one was put together by an outfit called PERTS, the Project for Educational Research That Scales. And I learned recently in kind of putting together the IRB proposal that the original version of that survey that we're still using it's been like modified and it's not even available on the PERTS website anymore. And I was like, well, we have old stuff, like we can do compare contrast, and I wish I'd talked to you first, but here we are.
Yeah.
So yeah, the project was sort of a last minute thing because we got, at the end of the summer, we were kind of gifted in a sense, as the chemistry department, some money to help students returning to in-person instruction from 18 months away. And so we thought this might be an idea or an opportunity to collect some data. And so we developed a scheme for helping to support students learn how to learn. And then we're kind of doing some surveys, these surveys 3 times during the quarter for all participating 100 and 200 level instructors. So
Okay.
at least we'll have a lot of bad data, like a large bad data set.
We've known all along that like we're going to have a really hard time comparing like what our learn how to learn impact is versus you've had 18 months of online learning. Like those are so intertwined at this point that like we've known from the outset that was going to be really difficult to frame. And so I think our goal with using the same surveys we had been using historically and have long-term data sets is at least we do have that idea of continuity between these are students in this department, in this course series.
Yeah.
Their lives have changed, everybody's lives have changed, but hopefully we're still capturing the same general population as it moves through the world that we're living in.
Yeah. Yeah, I mean, there's definitely more of a bet than, like I said, that it's, you know, you may see very different responses now in the students, but that's meaningful, right? It's probably not a measurement thing. It's just that we're in a very different environment, and that's actually what you're trying to measure. Um, and I think, you know, when it comes to interpreting your data or writing that for publication is just being aware of that and acknowledging it in a paper and saying like, hey, you know, this is something that's been used. We've done what we thought we needed to do, and you know, this is the world that we live in, and we're still going to try to run the statistics that we can. How many? So, you know, when I was showing sort of the CFA things, like the real minimum if you're going to run CFAs is 4 items per. So, you know, don't be afraid to drop items if you have more than 4. If you have some statistical data that says, hey, two of these items aren't really working anymore, but you also have to go back to, if you have access to the raw archival data, kind of do the same thing if you're going to start making comparisons, because, you know, I'm never afraid to drop items if we have many of them, and sometimes we have some instruments are developed with way more items than we actually need.
We definitely have like at least, I think we have 8 in the expectations about learning chemistry survey.
Okay.
But the problem with the other one is that it's 4 constructs, and 3 of the constructs only have 4 items, and the 4th has 3. So, and this was a problem that came up when my former colleague was writing the paper. Is one of the reviewers requested that she do a CFA, and I don't remember how they handled the 3-item construct. But yeah, I remember that coming up in the conversation. So I'm like, too bad for you. And then I went on with my life, and now here I am. So
yeah, you can do it with 3. You can't do it with less than 3, but at 3, then you have to say, I have to force my model to be tau equivalent, which means every one of the factor loadings is no longer estimated. I'm going to estimate them all to be the same.
right.
So that's no longer a variable, your factor loadings. When we go to 4, now we can say factor loadings are a variable and you only fix one of them to 1.
Yeah.
You leave the other ones as estimated. And but you can only do that when you have 4 items. If you go down to 3, then you can't estimate that number of parameters anymore. So it's a way to get away with 3 is not ideal, but you can still get CFA data. It's just, if you have the means to do better, you can, but that's kind of the fail safe, that if you have to get rid of an item, 3 is still good. And if you're in multi-factor things, then you don't have that limitation, because you have more degrees of freedom in your model to estimate, and it's
Right.
not as problematic. So,
Well,
so you said belonging, are you guys looking at specifically course level belonging?
well,
How are the items framed?
I wish I had talked to you before we did this. We really did it at the last minute. And so the belonging items, I think they're general. They're just, I think it's worded in terms of like, I feel like I belong in this course. I feel like I'm welcomed in this course. I think it's worded like that.
Yeah.
Okay.
Good.
Yeah.
Yeah.
All right.
I think those are much more meaningful, at least for the things that we generally look at, than, you know, some of the other ones are on major and things like that.
Right.
So.
Right. Do you remember, Sam? Is it? Yeah.
I don't. We could pull them up like out of that file, but I don't have them off the top of my head. There's 3 weeks of teaching in my head. The exact wording is long gone. Yeah.
Yeah.
Okay.
If you haven't seen it though, Colleen, look in JCE for the mindset paper that Swazet and I published. When you start looking at the data, I imagine that the mindset items you're using are like the typical Dweck mindset items about like belief, you know, ability and intelligence. The word intelligence isn't super interpretable when it comes to chemistry students, and we started replacing it with ability and really defining what ability in chemistry means. But that's, you know, very, very new, and there's some people in biology education starting to drive that forward, that the reason that we're doing it is a lot of times, you know, mindset's been a thing for so long now that what we think we're getting is a lot of socially desirable responses out of students is that you put an item in front of them, whether they actually believe that or not, they're answering in the way that they think that they should be answering. Because when we interview students, and this is what the paper shows, we interview students about what intelligence means when we're talking about intelligence in this chemistry class, and we can see that we've got students across the spectrum of mindset. But when we give them the items are heavily grouped into, well, everyone has a growth mindset. And we're like, well, everyone doesn't have a growth mindset. And we have contrasting data that says in our interview participants will tell you, no, I don't have the skills it takes to be successful in this course. I don't have it, right? They will very much tell you that, but it doesn't come across in forced response things, because I think we've been doing it for so long, and it's such a general thing now that they know what they're being measured on. And so we have to start changing up how we actually define that if we actually want to see that spread in the data quantitatively that we get when we actually talk to students about what they think about the course.
Yeah, that's really, I will definitely look up that paper. That's very, very smart, because it's part of what we're trying to support on our students is, you can grow your brain and like all that, stuff. And I keep thinking like, I totally have a growth mindset. Like I'm a teacher and like, I have learned things over time, but then I'll catch myself in a context where I'm like, I can't do it. And, like, so is it context dependent? Maybe. It's not universal. And so the students have to be the same. So
yep.
Yeah, that's very interesting. Thank you for bringing that up. Let me just acknowledge it's 4:50, and let's see, Lutz and Mitiku and Jennifer, you've been very, and Amgad has been very patient as we just have like caught up on our particular research project, me and Sam. But let me see if there's any last minute questions if you are still at your computer, or if you wandered away with your video off. Do you have anything before we say goodbye?
No, I'm good. Thank you very much. That was really, really, really interesting.
Yeah,
Yes.
thank you for attending and sticking around.
Absolutely. Yeah, thank you so much
for this talk. It was great.
Great.
Thank you,
Wonderful.
Jennifer.
Thank you.
Yeah, and I forgot, as I said at the top, I was going to have people put their affiliation in the chat. I totally forgot, but we did have a number of biology ed folks, such as Jennifer. I think we had a number of graduate students from Chem on the call, our philosopher friend, and there were a bunch of names I didn't recognize at all. So maybe they were from, I also sent this to our eScience group, just on who do a lot of big data stuff. And so hopefully we had some attendees from that. Anyway, thank you again,
Great.
Jack.
Yeah,
I learned a
absolutely.
lot. It's so great to connect. And thanks for doing this, kicking
All
off
right.
a great year.
Thank you again
Great
for
talk.
the invitation.
Thank you.
Thank you very much.
Bye. Have a
Good night.
Bye, everyone.